another force acting on it. There's a force acting that way on the mass when it hits the spring. It is a normal force, but coming from the spring, it is a conservative one, generally called the elastic force or the spring force. So energy is conserved. 1/2 mv initial squared plus, what is the formula for potential energy associated with the spring force?
Negative K delta X?
That's the force itself.
Okay.
What is the potential energy? Some people notice a similarity between that and the formula for kinetic energy.
Is it 1/2 K delta X squared?
That's the one. K is the spring constant. This K, this is a lowercase k. Delta X is how much the spring is displaced from equilibrium. It is the same process as we did before, we just have a different potential energy formula. What can we get rid of? What can we cancel out? Is there anything we can get rid of from every term? Yeah. We multiply everything by 2, it goes away. All right, the remaining stuff. Now, if you want to put MGH in here, that's fine. There's no harm in that. It's just unnecessary because it's not changing height at all, so it's going to cancel out with itself. All right, but what can we get rid of here?
What does the problem ask for this one?
How much will the spring compress? If B hits the spring, how much will it compress?
Is it possible to take out the square?
No. Not legitimately. Or I guess if you did, it'd become far more complicated. B is going to stick to the spring. What's the maximum compression? Now, why do I need B to stick to the spring? This comes from an old test, and B sticking to the spring would lead to a problem dealing with harmonic motion, which we haven't covered yet. So that's why it's sticking.
Is final velocity 0?
Yes. At maximum compression, the mass B stops. If it hadn't stopped, it's not maximum compression. And we can get rid of one more term.
The initial displacement?
Yes. The spring is just sitting there. So we have now reduced this to a much simpler. Mass times initial speed squared is equal to K times the displacement, final displacement squared. Solve for final displacement. Now we could get rid of the square if we wanted to, because I don't have any additional terms there. But we just solve for delta x, final, that is the square root mv initial squared over k, which is the square root of m over k times the initial speed.
What is the coefficient of spring?
Oh, I guess I didn't give it. Let's make A equal to, oh, did not want to repeat that number. Again, 45 there, let's make it 30 here. 30 newtons per meter. Which basically is saying that it takes 30 newtons to compress it or stretch it 1 meter. It'll take 60 newtons to do it 2 meters. 90 newtons to do 3 meters. And so this is the square root of 7/30 times 10.18. Uh, 2.4.
I got 4.92 meters.
4.92. Oh, I forgot to do the square root. 4.92
Yes.
meters. Questions here? And then the last part is, instead of the perfectly elastic collision, suppose it were perfectly inelastic, how fast would it be going after the collision and how much would the spring compress? Well, it'd be convenient to keep this up. That equation's still going to hold true. The mass will change, but that doesn't affect this. So we'll go back to here. So they're going to stick together. I've got the Ford cruising along at 14 meters per second. Going to hit the 7, which is initially at rest. So I have 56 units of momentum before, which means that's the final momentum. And so that'll be 11 times V final. Which is 5.09 repeating meters per second. And so that equation, this equation still holds true because we didn't plug numbers in too early. We can just change the numbers, use the same equation. So the spring will now compress square root of 11/30 times 5.09. So even though we increased the mass, the speed dropped off, or velocity lessened, the speed lessened. And so it did not compress as much. Questions? Ethan, you would have initially brought this up. Are you good?
Yeah.
Yep. Other questions?
You would just use all the same methods, but it would get totally different answers and numbers.
Yeah.
Without this. Okay.
Yeah. All right. Well, there is much.
You said 56 newtons times seconds?
Newton seconds. The units for momentum. Remember that impulse is force times time or change in momentum. So the units of force times time would have the same units as momentum. So force units and times units.
Okay.
Or, since a Newton is a kilogram meter per second squared, if I multiply times seconds, that's a kilogram meter per second, which is a mass times a speed unit. How's there any close the door on this? Okay. We have dealt so far, other than centripetal motion, with linear motion. We've dealt with acceleration because of change in speed and acceleration because of change in direction, but now we sort of have to deal with rotational motion. And we can basically double the number of formulas we have right now. Because there's an analog, so I got a linear / translational. Linear and translational mean the exact same thing, just depending on context. Just as angular and rotational can be used interchangeably as well. As I believe stated in the video, tradition just associates usually one word or another. You generally talk about angular velocity instead of rotational velocity, just because that's the habit people got into. But if we're talking about position, the analog over here is angle. Displacement. Angular displacement. Although the language generally doesn't, you don't see it written as angular displacement. It's generally wheels rotating through what angle does it rotate. Velocity. Angular velocity. Acceleration. Anyone want to take a shot at it?
Angular acceleration.
There you go. In terms of the symbols used, because frankly, I don't feel like writing those words out all the time. For position, we have the X, Y, R, Z, S. Displacement, we just put a delta in front of it. Velocity and acceleration for the vector quantity. Over here, typically, although definitely we will see exceptions to it, but oftentimes for the rotational stuff, the Greek letters are used. So angle, theta, and phi are probably the two most common ones. Alpha, beta. They are vectors. Angular displacement, you stick a delta in front of whichever one you're using. Angular velocity, omega. With centripetal motion, we dealt with angular speed, which was just plain old omega. Looks kind of like a W, but it's not a W. And angular acceleration, alpha. The rock is thrown upward. at an initial velocity of, we make a speed directions indicator right there. Initial speed of 30 meters per second. At what time does the rock reach 10 meters?
Are you able to have alpha in both the angle and the angular acceleration?
No, thank you. That. We'll keep that out for now. Yeah, I guess when I've used alpha and beta before, we were not dealing with angular motion, so yes, thank you. Questions? Other questions or comments? All right, we have a chapter 2 problem here. We'll set up delta x, s, whatever you use, vi, vf, a, and t. What do we know?
Initial speed.
What's initial speed?
30 meters per second.
So initial velocity, 30 meters per second?
Yeah, that's what I meant.
Okay. So we've now established up is positive.
And displacement's 10.
At 10 meters.
Negative 9.8 is acceleration. Right? It's going, yeah, negative 9.8.
I assume you were saying 9.8.
Yeah.
All right. We have 3 things. We can find time. It's a constant acceleration problem, so we've got the cake formulas. They don't deserve to hear anything we're doing. So which formula?
Displacement equals VIT plus 1/2 AT squared.
All right. So 10 is equal to 30t minus 4.9 t squared. And it's a quadratic, so 4.9 t squared minus 30t plus 10 equals 0. T is equal to 30 plus or minus the square root of 900 minus 4 times 4.9 times 10 divided by 9.8, which is, we got 2 answers here. I would expect both answers to be positive.
I got 5.77 seconds. 10.354 seconds.
Okay. Which one is correct?
The smaller number?
Both. Why the smaller number?
Because it's saying it's gonna go up and then past 10 meters and
Right.
then come back down to 10 meters. So at what time does the rock reach 10 meters? I'm assuming that means for the first time.
Ah, okay. I was going for both being correct, but I hear what you're saying. All right. Chapter 2 problem. Hopefully you're comfortable enough with that. Let's make a chapter 9 problem. at 30 radians per second. With a uniform acceleration of negative 9.8 radians per second squared. At what time has the wheel rotated in radians? So what's the answer?
3.54 seconds.
Yes. It is the exact same math as we did over here. The only difference is if I have a wheel that rotates around twice and then comes back twice, it hasn't really rotated 0 times. So that is one difference between the rotation and the linear. We would set up the exact same way, except now delta theta, omega initial, omega final, alpha, and time. That's negative 9.8 radians per second squared. That is 30 radians per second. And again, radians. And then you plug in basically the exact same equation. So for any of these chapter 2 problem equations, all we do is just stick in the rotational analog. So that equation becomes delta theta is equal to omega it plus 1/2 alpha t squared.